Hello, hello, hello. Can I hear myself? Can I hear myself? Hello, hello, hello. Not yet. Okay, I can hear myself. That's great. Cool. Okay. I have a plan today. The plan is to research this tool called Chem Tool. And the reason being is that I want to know how to read these diagrams. So this one, for example, says, let me just see if you can see this, cytosine, guanine, adenine, uracil, all these things. Um, I'd like to know what the individual kind of symbols mean inside those diagrams. So I thought it might be interesting to check out the actual tools used to make these. And one of them I saw was called Chem Tool, a small program. You can't see that. Small program for drawing chemical structures on Linux and Unix systems using the GTK toolkit. Uh, Maybe it's not available in Windows actually, but we'll find something else as well, I'm sure. Um, anyway, that's the goal. So I'm just going to quickly start with a Duolingo lesson on Greek, which I'll fail massively at, I'm sure. Here we go. Let's go back to Greek. Okay, right. I don't really remember much from the last time, but let's see how this goes.
Ro,
Ro. Okay, so P is the R,
ro,
remember. Ro. Oh, this is a bit too big. There you go. Yeah. Mark the carrot. Well, we've got the P there, so that's the
mar,
R there. To is the,
to,
and then carrot has got to be that. Carotto.
caroto,
Carotto. All right.
nana, tonero,
Nana.
nana,
So
nana,
the V is an N. Actually, let me just listen to this. Okay, you can hear it. Okay, cool. Yeah, V is an N, so that is going to be Nana. The Nero. Nero means water, I think. So yeah, I wonder. Cafe water. Maybe that's what that means. Cafe Nero. I don't know. They're probably not related at all. Nana. So that's going to be this one.
nana,
To
to,
Nero. Nero.
nero, pan,
Oh, I just realised I've told no one I'm doing this, so I'm going to have a very lonely session again. So let me see if I can communicate around. It's okay. I quite like to not have um too many people watching. But anyway, okie dokie, cool. What did she say?
pan, pan,
Anne.
pan,
Okay, cool. There's the A, there's the V for the N. Mark, Mark. P,
mar,
Arra. To,
to,
Nero,
nero,
Nero. Write this in Greek. Nana. So, oh gosh, I need the Greek keyword up. How do I do this? On screen. Ooh. On screen. Keyboard. Okay. Yes, we need that. Greek. Okie dokie. So Nana is going to be, and I think this was actually capital N. Yeah, it is capital N. So if I go here, there it is. Na, and then it's going to be V. Nana. And then it'll be to, to, and then ka, ro, to. And I think this had, whoa! Whoops. I think this had, wait, how do I get the graphics up? Oh, I don't know. Well, I'm sure it'll be fine. Caroto. I don't know how to get the other graphics up. No idea. And I would have got it wrong anyway. Okay, cool. So that's one lesson. I'll do one more of those, and then we'll try the Chem Tools out.
Ria.
Ria. What do you hear, Ria?
Ria.
Okay. Yes, that's. Oh, okay. Nai.
Ne.
Ne. Okay, ne. To.
To.
Mini. Oh, it's gonna have an N in there somewhere. Mini. It's gonna probably be this.
Mini.
Mini. Okay. And then market's gonna be a P. And then a K. Yep. Market.
Market.
So, ne. To. What was that again? Me. Mini. Market. That's an M. Okay.
Ma.
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 Anna and Mark. Okay. Anna.
Anna.
Oh, interesting little tick there. Not seen that before. To, Nay.
Ne.
Mark.
Mark.
Ah! Oh, it's oh, okay, so it's changed. I think it's changed. Yeah. So I wonder what the difference is between these two. Let's have a little discuss here. Let me have a look. Okay, I don't know.
Ne.
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 Mark and Maria. Mark?
Mark.
And it's gonna be K, okay.
Che.
Maria.
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 Ne. Ne. Ne.
Ne. Anna and Mark. So this is Anna,
Anna.
K,
Che.
Mark.
Mark.
Alright, we're done. Okay, so back to work. Chem Tools. So yeah, I want to try and figure out how these diagrams work. So let's go check out this Chem Tool. See if we can download like a Windows version of it. This is currently just typical bug fixes. It was compiled on Linux with the help of MXO and appears to work on at least Windows 7 and Windows Server. Okay, no, this does not mean I intend to switch to Windows, as it currently does not. Okay, well maybe there's a Windows chemical diagram tool, or maybe online. Online. PubChem Sketcher. That sounds good. Ah. Okay. This actually looks pretty good. I was kind of hoping for something with a bit of bit of help in it. Broadband and dial-up. I think the very fact that it's got dial-up in the name means it's probably a little out of date. Let's see, Chem Spider. Let's try that one. Ooh, this looks pretty. Draw structure. Oh yeah, yeah, yeah. We like this. Ah, is that figuring out what it must be for us, or is that? Okay, this actually looks pretty good. Let's try this. Oh, delete does not do anything. Let's try this one. Zoom out. No. Trash. Erase. There you go. So, is there any help on this? Let's have a look. Simple. Structure. Search and share chemistry. Advanced. Help. See what this says. can you see this again? Never so sure. Yeah, kind of. ChemSpider is a web-based database of small molecules with associated data and links. The site is free to use, and you can search and access all of the available data on the site without registering on an account. The data in ChemSpider has been supplied by various institutions and commercial companies. Data in ChemSpider is created on an ongoing basis by ChemSpider staff and users to ensure data integrity and data quality. ChemSpider has a wide user base which includes students, teachers, lecturers, scientists, blah blah blah. Okay, cool. We can help you find important data such as chemical structures. Find data on ChemSpider, names, search, systematic names, synonyms. Let's have a look at this. Let's go hydrogen. Let's do uh, ribonic acid, yeah. Okay, cool. Okay. So it's got 5 or whatever C. Oh, yeah. We also need to know these symbols now, so I'm guessing that's the periodic table. Hehe, this is cool. This is really taking me back to school. Nothing better than feeling like you're back at school. Nah. Um, Carbon. Okay, we know we need a sexy periodic table. This is periodic table. Must be a really nice one somewhere. Can I zoom this in? Oh yeah. Oh, and it gives us loads of information as well. Okay, let's split the screen a bit. Put that there. Put that there. Okay, so in this case, there's 5 carbons, 9, I guess, hydrogens. Let's just double check. Hydrogen, yes. And then 6 oxygens. Oh, yes, makes sense. Now what does this actually say? It says key isotopes 1H, 2H. Is there any helpers here? What these mean? History, home, alchemy, podcast, video trends. Ooh, let's try that one. Blah blah. Podcast, video trends. Anything here? Help. Oh, I need some help. Okay. How to read a periodic table. I can't remember anything about this stuff, so it's all interesting to me. If you find the periodic table confusing, difficult to understand, you're not alone. Good. Understanding how it works can be hard. Ah, that's not a very, not a very good thing to know. But learning how to read it will help you be successful in the sciences. Start by recognizing the structure of the periodic table and what this tells you about each element. Okay. Struct. So we've got some kind of coloring here. Hydrogen. And then number 2 is a different color. Let's see the comparison here. You've got electron configuration 1s1, 1s2, 2s1, 2s2, 2s2s, 2s2p1. Okay, so this is going to go 3, 4. So all getting bigger. Okay, so electron configuration is getting bigger as we go down. Interesting. Yep. And density, is that... Are they all getting bigger? No. No, because that's 11 and that goes down again, so it's not that. So it might be due to electron configuration. Okay, so let's have a look. Next, you can study each element. Finally, use the information provided in the periodic table to find the number of neutrons in an atom. Recognizing the structure of the table. Okay. Read the periodic table from top left to bottom right. The elements are ordered by the atomic numbers. Okay. atomic numbers. But this looks like a more fancy periodic table. What is this number here? Helium has 4003. Where is that number in here? Oh, I see. Ah, okay. I see. Oh, that's cool. I like that. Interesting. How do I turn it back? Okay. Ha! Okay. The atomic number is how many protons the element's atom possesses. You'll also notice that each element's atomic mass increases as you move across the table. Okay, so how many protons the element's atom has? Density, electron configuration, proton. Let me just be double sure I know what a proton is. A stable subatomic particle occurring in all atomic nuclei with a positive electric charge equal in magnitude to that of an electron. Okay. Simple definition, we like simple. An elementary dear Watson, that is identical with the nucleus of the hydrogen atom. That is identical with the nucleus of the hydrogen atom. An elementary particle that is identical with the nucleus of the hydrogen atom. That along with the neutron is how is this simple? It's not simple. I want baby speak. Let's try this. Proton is a subatomic particle. Cool. It's smaller than an atom. Symbol P or P plus with a positive electric charge of +1. Where's that? Euler. It can't be Euler. Electron. +1 electron. Okay. Elementary charge. The elementary charge usually denoted by E. There you go. Elementary charge. Okay. +1 E elementary charge and a mass slightly less than that of a neutron. So a proton is a subatomic particle, symbol P or P plus, with a positive electric charge and a mass slightly less than that of a neutron. Okay, cool. So the atomic number is how many protons the element's atom possesses. You'll also notice that each element's atomic mass increases as you move across the table. Okay, let's go see that. I can barely see what that says. Just try and... It's covering the screen. So, mass, let me see. Where is the mass here? Density was density is g centimeters to the power of -3. So this is going to go 0.0. Okay, 5, 9, 22. Yeah, we already figured this out. It doesn't go in that order. Okay. Okay. Atomic numbers. Okay, so ordered by atomic numbers. Atomic number is how many protons the element's atom possesses. So hydrogen has just over 1, and helium is just over 4. Interesting. This means you can tell us a lot about an element's weight by just looking at its place on the table. Sorry, coffee time. The atomic mass increases as you move across or down the table because the mass is calculated by adding up the protons and neutrons in each element's atom. The number of protons increases with each element, which means the weight goes up as well. Electrons are not included in the atomic mass as they contribute much less to the atom's weight than protons and neutrons. Neutron. Pro means with, nu means without, I'm guessing. Let's have a look. Etymology of neutron. neutral. Okay. Uh, Electrically neuter particle of the atom from neutral. First record of okay, cool. So electrons are not included in the atomic as they contribute much less to the atom's weight than protons and neutrons. So increasing order and then rare earth element, okay. And then you have increasing order. 2. Observe that each element contains one more proton than its predecessor. You can tell this by looking at the atomic number. Atomic numbers are ordered from left to right. Since the elements are also arranged by group, you will see gaps on the table. For example, the first row contains hydrogen, which is an atomic number of 1, and helium, which has an atomic number of 2. However, they are at opposite ends of the table as they are in different groups. Oh, did these actually go 13, 18, 22, 33? I don't know what this means then, yeah. It's nice that they tell you. I mean, make me work for it, why don't you? Okay, so group is down, order is right. So let's have a look at the grouping here. Yeah, okay. Recognize groups which share physical and chemical properties. Groups, also known as families, fall in a vertical column. In most cases, groups will share the same color as well. This helps you identify which elements have similar physical and chemical properties to each other, which allows you to predict how they'll behave. Each element in a particular group has the same number of electrons in its outer orbital. Okay. So at the moment I'm thinking, oh, I know this is such elementary stuff, but at the moment I'm considering it to be like this sort of thing, and it just said this helps you identify which elements have similar physical and chemical properties to each other, which allow to predict each element in particular has the same number of electrons in its outer orbital. So each element in a particular group has the same number of electrons in its outer orbital. So let's say this group, electron configuration 2s, 3s, 4s, 5s, 6s, 7s, 2, 3, 4, 5, 6, 7. I'm looking at the electron configuration. 3, 4, 5, 6. Yeah, we get the point, I think. It's interesting. Why does it have to use these things and not explain it? I don't think it has a legend here. No, okay. Most elements fall into one group, but hydrogen can be placed with the halogen family or the alkali metals. On some charts, it will appear with both. In most cases, the columns will be numbered 1 to 18. The columns will be numbered 1 to 18. Three, 6, 9, 12, 15, 18. Okay. 18 columns. Either above or below the table, the numbers may be shown in Roman numerals, Arabic numerals, or numerals. Does this one have that? No. Okay. How do you reset this? Clear filters, okay. When you go down a group from top to bottom, it's called reading down a group. Okay. So, yeah. Notice why gaps exist in the table. Although elements are ordered based on their atomic number, they're also arranged into groups and families that share the same physical and chemical properties. This helps you better understand how each element behaves. Since elements don't always fall neatly into groupings as they increase in number, the periodic table contains gaps. 57. Really? Xe, xenon. Yeah, then we go to cesium, then barium. Cesium, barium, then you got 57 to 71. Oh, I see. 57 to 71. Okay, I see. There is the gap. Okay. So, for example, the first three rows have gaps, as the transition metals don't appear in the table until atomic number 21. The transition metals don't appear on the table until atomic number 21. I don't understand what that means. Notice why gaps exist in the table. Although elements are ordered based on their atomic number, they're also arranged into groups and families that share the same physical and chemical properties. This helps you better understand how each element behaves. Since elements don't always fall neatly into groupings as they increase in number, the periodic table contains gaps. For example, the first three rows have gaps, as the transition metals don't appear on the table until atomic number 21. I see calcium, potassium, and then it goes to scandium, titanium, all these metals. Ha! Okay. Metal. Non-metal. I don't understand what that means. Transition metal. I wonder if they think that you're supposed to know what that means. Or if someone just wrote it because they were told and don't really understand it themselves. I hate things like that, I really do. It's not the person writing it's fault, it's just, I guess you can't cover everyone's stupidity like mine. Similarly, elements 57 through 71, which are the rare earth elements, are usually pictured as a subset at the bottom right of the table. Oh, I see. Okay, so here's the missing ones. Europium. This is a joke. This one's interesting. Samarium. Dysprosium. Interesting. Notice that each row is called a period. All of the elements in a period have the same number of atomic orbitals, which is where their electrons go. The number of orbitals will match the number of the period. There are 7 rows, meaning that there are 7 periods. I'm not sure I understand that either. For example, the elements in the period 1 have 1 orbital, while the elements in period 7 have 7 orbitals. Period 1, 1 orbital. 1 orbital electron configuration. I wonder if that's what it means. Yeah, 3, 4, 5, 6, 7. Okay, yeah. I wonder what the to the power of 2 is, and what the S is. So 5F, 6D, 7S. I don't know. In most cases, they're numbered 1 to 7 down the left-hand side of the table. When you move across a row from left to right, it's called reading across a period. Metals, non-metals, semi-metals. Okay. Distinguish between metals, semi-metals, and non-metals. You can better understand the properties of an element by recognizing what type of element it is. Fortunately, most periodic tables use color to indicate whether the element is a metal, semi-metal, or non-metal. You'll notice that metals occur to the left of the table, while non-metals fall on the right. Semi-metals are sandwiched between them. Keep in mind that hydrogen can be grouped with either the halogens or the alkali metals because of its properties, so it may appear on either side of the table or may be colored differently. Elements are labeled as a metal if they have luster, are solid at room temperature, conduct heat and electricity, and are malleable and ductile. Elements are considered a non-metal if they lack luster, don't conduct heat or electricity, and are non-malleable. These elements are usually gases at room temperature, but may also become a solid or liquid at certain temperatures. Elements are labelled as semi-metals if they have a mixture of properties of both metals and non-metals. Cool. Studying the elements. Let me just see if I can remember this. So this is the period is this line. They go down, so this will be how many electrons in the orbit increase as you go down. And then the metals are typically over to the left. Then you've got the semi ones around here. I'm guessing these. Let me just check this out again. Yeah, silicon, germanium, okay. And then you've got the non-metals here. Right. Okay, fine. Let's go back down. It most often appears in the center of the box in a large font. The symbol abbreviates the element's name, which is standardized across different languages. When you're doing experiments or working with elemental equations, you'll likely use the element's symbols, so it's important to familiarize yourself with them. Uh-oh. This symbol is usually derived from the Latin form of the element's name, but it may be derived from the widely accepted common name, especially for newer elements. For example, the symbol for helium is He, which closely resembles the common name. However, the symbol for iron is Fe, which is harder to recognize at first. Was that Greek, did it say? Or Latin? Latin. Where did it say that again? There, haha, okay. Common name, carbon. Look for the full name of the element, if it's present. This is the name of the element that you will use when writing it out. For example, helium and carbon are the names of elements. In most cases, this will appear just below the symbol, but its placement can vary. So in this table, it just says it when you hover over. Some periodic tables may omit the full name, using just the symbol. Atomic number is 6. So carbon C, atomic number 6, okay. Find the atomic number. The atomic number is often located at the top of the box, either in the center or the corner. However, it could be located under the element symbol name. Atomic numbers run sequentially from 1 to 118. The atomic number will be a whole number, not a decimal. Okay. So that this is what I was doing before with that 1.008 on the hydrogen to the right there, and this one has 4.004. That means something else. Interestingly, if you go to the key isotopes, it's got 9.012, which is 9Be, and then you've got 6.94, which is 7Li. That doesn't work like that, okay. Yeah, no, yeah, 4.003 for helium. One, and let's have a look at this one. 51, that's got, yeah, so it's like rounding up with the key isotopes number. It's rounding up that number bottom right. So they must be related. Yeah, definitely. I wonder what that actually means then. Like, why is it okay to round it here? Is this just like a notation and then this is the actual value? And what is this value? you know, without the Cu, key isotopes. Okay, fine. We'll figure that out. So, carbon has 1, 2, 3, 4, 5, 6 nucleus. Okay. Uh, no, it has 6 protons. And its protons are the nucleus. Let's have a look. The central and most important part of an object, movement, or group, forming the basis for its activity and growth. That's not very helpful. The atomic nucleus is the small, dense region consisting of protons and neutrons at the center of an atom. Consisting of protons and neutrons, okay. I wonder what these are supposed to represent. So if I were to try and draw, yeah, let's just see if I can do it from memory. So carbon has 6, what are they called again? 6. It has an atomic number of 6. Okay. Atom is the entire thing though, isn't it? The smallest particle of a chemical element that can exist. Okay. So it's made up of 6 of these particles, and these particles are protons or neutrons. So in terms of carbon, that would be, you have your central place, and you have one, oh, does it say what's positive and what's negative? Or neutral? No, it does not. So I wonder if that means they're all just positive protons. So carbon is like that, and then it says electron configuration is 2 protons to the power of 2? That doesn't make sense. I don't know. Okay, fine. Anyone here to help? Am I just on my own again? On my own. Cool, that's always fun. Right, let's carry on. So it says the atomic number is located at the top of the box, even the center of the corner. However, it could be located under the element 100. The atomic number will be a whole number, not a decimal. So in this case it's protons, but I actually wonder, yeah, electrons. And these are negative charges going around it. Recognize the atomic number is the number of protons in an atom. Okay, it is the number of protons in an atom. So 6 equals protons equals atomic number. Okay, cool. All of an element's atoms contain the same number of protons. Unlike with electrons, an atom cannot gain or lose protons. Otherwise, the element would change. You will use the atomic number to find the number of electrons and neutrons as well. So, if there are 6 protons, then there must be 6 electrons. Okay, cool. This makes sense. So, the way they've drawn it is 2 of these. And you've got 1, 2, 3, 4, 5. It's interesting how they've balanced it out as well. 5, 6 in some way. 6 protons. These are no, these are electrons. Electrons. Can you see this? I doubt you can. You can, okay. Electrons. Whoa. And then it's count of electrons must be equal to count of protons, otherwise the imbalance would cause the element to change to another element or something. Let's just reread this. The atomic number is the number of protons in an atom. All of the atoms contain the same number of protons. All of an element's atoms contain the same number of protons. Unlike with electrons, an atom cannot gain or lose protons. Otherwise, the element would change. You'll use the atomic number to find the number of electrons and neutrons as well. No, no elements contain the same number of electrons as protons. There is an exception if they're ionized. Ha. Let's draw that one. Unless ionized. Cool. Protons have a positive charge and electrons have a negative charge. Since regular atoms don't have an electrical charge, that means electrons and protons are equal. However, an atom can lose or gain electrons, which makes it ionized. Okay, so information blue. If an if an if an element gains protons or electrons, it becomes ionized. Ions are electrically charged. If an ion has more protons, it is positive, which is indicated with a positive sign next to the ion's symbol. If it has more electrons, the ion is negative, which is indicated with a negative symbol. You will not see a plus or minus symbol if the element is not an ion. Okay, let's see if I guess none of these are ions because otherwise there would be something else. I'm not sure. Ooh. Okay, using the atomic weight to calculate neutrons. Ah, okay, the atomic weight. Find the atomic weight. The atomic weight usually appears at the bottom of the box, below the element symbol. So carbon has 12.011. That's what it is. Haha, we got it. Finally got to that bloody information. Weight of the... Oh no, how did I do that? Undo close. Weight, the atomic weight. So this is constituted by how many protons and electrons, I guess maybe neutrons as well. So atomic weight represents the combined weight of the particles in the nucleus, which includes protons and neutrons. Okay. However, ions complicate the calculations, so the atomic weight represents an average of the atomic mass of the element and the atomic mass of its ions. Because the weights are averaged, most elements will have atomic weights that include decimals. Although it may appear as though the atomic weight increases in number from top left to bottom right, this is not true in all cases. Yeah. Well, we saw that, I think, because we went 47, 69, 83, 91, 101. Actually. No, I don't think we did see this. Okay, well, let's see if... Interesting. I'd like an example. Determine the mass number of the element you're studying. You can find the mass number by rounding the atomic mass to the nearest whole number. The mass number. This accounts for the fact that the atomic weight is an average of all possible atomic masses for that. Ooh, okay. You can find the mass number by rounding the atomic mass to the nearest whole number. So the atomic mass, 28, whole number is 28. So I wish I could, can I click on it? Okay. I don't want to see that yet. 28 SI. Okay, so you can find the mass number by rounding the atomic mass to the nearest whole number. This accounts for the fact that the atomic weight is an average of all possible atomic masses for that element, including ions. For example, the atomic weight of carbon is 12,011, which rounds to 12. Similarly, the weight of iron is 55.847, which rounds to 56. Subtract the atomic number from the mass number to find the neutrons. Okay, atomic number from the mass number. So hydrogen has, let's open up another. In fact, let me just record this first. Whoa, big. Didn't want that. Okay, cool. So wrong one, this one. So it says that if I take hydrogen's mass, which is 1.008, 1.008, which is hydrogen's mass, and then I minus the atomic number, which is 1, the neutrons will equal 0.008. What are they doing this with? The mass number is calculated by adding together the number of protons and neutrons. Oh, the mass number is calculated by adding together the number of protons. So with hydrogen, you've got 1 proton plus 1 electron. But in this case we've got, yeah, okay, this makes sense. That's wrong. 1 proton plus 1 plus essentially it's just the negative of that. I see. Cool. Together protons and neutrons will give you the mass number. This allows you to easily find the number of neutrons in an atom by subtracting the number of protons from the mass number. Use this formula: neutrons equals mass number minus protons. For example, carbon's mass. Okay, let's see if we can do carbon. So carbon's over here. It's going to be 0.11 neutrons. Carbon's mass number is 12. Are we in agreement? It's 12.011. Mass equals 12.011. And it has 6 protons because there are 6 protons and 6 electrons. 6 protons and 6 electrons. Atomic number 12 atomic number. So neutrons will be protons take away take away the mass, was it? The mass number is mass number minus protons. Okay, so it's 12.011 take away 6 equals 6.011 or 5.9 or whatever it is. I don't know. What is that? So carbon's mass number is 12 and it has 6 protons. So carbon's mass number is, it's not 12. I guess it's the average. So it's atomic number it's talking about, and it has 6 protons. Cool. Since 12 minus 6 equals 6, you know carbon has 6 neutrons. For another example, iron's mass. Let's try iron then, just to double check. So Fe has 55.845. 55.845 is the mass. It then has 56 atomic number, and that means that it has 23. No, it doesn't. God, I'm terrible at maths. I really am. 28 protons and 28 electrons, and the neutrons are 55.845 take away 28, or 56 take away 28, and so 56 take away 28 is 28. That's not right. 56 take away 26, so, and it has 26 protons. So why does it have 26 protons then? This was for iron, right? Yeah. Fe. Fe has 55.845 mass. But it's saying the mass is 56. 56 minus 28 is 28. That's what I just did. And it says, it seems to think this has 26 protons. But if you had that, so 56 take away 26, it's going to be 30 electrons. So it must be an ionized thing, because they're not equal. I don't understand this. What am I missing here? I've missed something. Subtract the atomic number from the mass number to find the neutrons. So if I were to do that, it would be... See, this doesn't make sense. I swear. It just says... What? Determine the mass number of the element you're studying. So find the atomic weight. Oh! Weight versus mass. Sly dog. I wonder if it's that. The atomic weight usually appears at the bottom of the box below the element. The atomic weight represents the combined weight of the particles in the nucleus, which includes protons and neutrons. However, ions complicate the calculation, so the atomic weight represents an average of the atomic mass, of the element, and the atomic mass of its ions. Classic, classic, classic flaw in me reading things. The atomic weight represents the combined weight of particles in the nucleus, which includes protons and neutrons. However, ions complicate the calculation, so the atomic weight represents an average of the atomic mass of the element and the atomic mass of its ions. Because the weights are averaged, most elements will have atomic weights that include decimals. Although it may appear as though the atomic weight increases in number from top left to bottom right, this is not true in all cases. You can find the mass number by rounding the atomic mass to the nearest whole number. You can find the mass number by rounding the atomic mass to the nearest whole number. I see, okay. This accounts for the fact that the atomic weight is an average of all possible atomic masses for that element, including ions. I mean, does this mean with gravity mixed in? I don't know. For example, the atomic weight of carbon is 12.01, which rounds to 12. Similarly, the weight of iron is 58, which rounds to 56. So the atomic mass is 56 versus the atomic weight, which is 55 point. Okay. Yeah, atomic weight. Okay, cool. This makes sense now. So, let me not read this then. So let me just try this again. So the mass is going to be that, the weight, or the atomic number. This is the atomic weight, atomic mass, and then it says the number of protons are 26. But we found out up here that no elements contain the same number of electrons as protons. There is an exception if they're ionized. Protons have a positive charge and electrons have a negative charge. Since regular atoms don't have an electrical charge, that means electrons and protons are equal. However, an atom can lose or gain electrons, which makes it ionized. Electrons and protons, I see. So that means... I'm so confused. It kind of skips on here. Find the atomic weight, which we just read, and then we've got this, but it's saying the number of protons is 26. I'd like to know where it's got that from. Neutrons is equal to the mass minus the protons, which should be the mass. It says the atomic mass is the nearest number. That's the atomic weight, yeah. For another example, iron's mass number is 56 and it has 26 protons. Since 56 most of you have 30 neutrons. An atom's isotopes will contain a different number of neutrons, which changes the atom's weight. An atom's isotopes will contain a different number of neutrons. Oh, is that it? The atomic number is how many protons the element's atom possesses. So is iron... What? The atomic number is how many protons the element's atom possesses. Well, in that case, that would mean that there's 26. Ha! Okay. That makes a lot of sense now. Oh my god. Why did I completely skipped that. That's classic James. Classic me. Yeah. Okay, cool. That makes a lot of sense now. Protons equals atomic number. We knew this at the start and I forgot. Classic. Okie dokie. Okay, so now we know a bit more about this. Is there any more to this article? No. No, there is not. Tips. Reading the periodic is hard for many people. Don't feel bad if you're struggling to learn how to use it. Wah wah. Colors may vary, but the information is the same. Some periodic tables may simplify the information. For example, they may provide just the symbol and atomic number. Look for a table that meets your needs. Uh, is there a helping hand table? Okay, I think that was a little bit confusing, but we're good. So here's our thingamajiggy. Cool. So now, if I go back to our Chem tool, Chem Spider, is this not going to grab it in the center? Firefox, what are you doing? Okay, well, whatever. So let's take a look at a part of this. Let's start with cytosine. Let's do that. So cytosine. Comes to the right. So cytosine has one nitrogen, two helium, and some oxygen. 4 and 3 and 2 and 1. I wonder what they mean. Okay, and what are these diagrams called? Let's have a look. Let's have a look. What is this made in? Engineer Gina, own work. How to read chemical formulas? Let's have a look. No. Structures. Structural formula. The structural formula of a chemical formula is a graphic representation of the... Okay, this is good. The structural formula of a chemical compound is a graphic representation of the molecular structure determined by structural chemistry methods, showing how the atoms are possibly arranged in the real three-dimensional space. The chemical bonding within the molecule is also shown, either explicitly or implicitly. Unlike chemical formulas, which have a limited number of symbols and are capable of only limited descriptive power, structural formulas provide a more complete geometric representation of the molecular structure. For example, many chemical compounds exist in different isomeric forms. In chemistry, isomers are molecules or polyatomic ions. Many atomic ions with identical molecular formulas. So in chemistry, isomers are molecules or many atomic ions with identical molecular formulas. Okay, I'm not sure I quite understand what that means, but let's carry on. For example, many chemical compounds exist in different isomeric forms, which have different enantiomeric structures. Yep. Okay. In chemistry, an enantiomer is one of two. Oh my god! Ah, that's classic. Stereoisomers. Two isomer. I can't remember what mer means now. Etymology of mers. Isomers. Stereoisomers. Okay. Whoops. Etymology, please. Did I? Yeah. I'm looking for the etymology of this word. Isomerism. Stereo. is, oh, solid. Stereos, solid. Forming words relating to the solid, three-dimensional. I did not know that. That's really interesting. Specifically forming words relating to the binocular contribution to three-dimensional vision. Forming words relating to the solid, the hard. Oh wow, okay. And what does isomerism, isomer, noun, isomerism, the phenomenon of the existence of isomers, the existence of different substances with the same molecular formulae. Okay. Solid substance with the same molecular substances, uh, same molecular formula. Okay, trying to understand what it's saying here. So in chemistry, an enantiomer is one of two solid same formula structures that are mirror images of each other that are non-superposable, much as one's left and right hands are mirror images of each other that cannot appear identical simply by reorientation. Okay, cool. That makes some sense, amazingly. So which have different enantiomeric structures but the same chemical formula. Several systematic chemical naming formats, as in chemical databases, are used that are equivalent to and as powerful as geometric structures. These chemical nomenclature systems include SMILES, INCHL, and CML. SMILES, the Simplified Molecular Input Line Entry System, is a specification in the form of a line notation for describing the structure of chemical species using short ASCII strings. SMILES strings can be imported by most molecule editors for conversion back into two-dimensional drawings or three-dimensional models of the molecules. The original SMILES specification was initiated in the 1980s. It has since been modified and extended. In 2007, an open standard called OpenSMILES was developed in the open source chemistry community. Other linear notations include the Visvesser line notation, linear notations, Visvesser, Rosdal, and Sybil. Okay, cool. Let's see this one. The International Chemical Identifier, the IUPAC, International Union of Pure and Applied Chemistry, oof, okay, is a textual identifier for chemical substances designed to provide a standard way to encode molecular information and to facilitate the search for such information in databases and on the web. Initially developed by the Union and National Institute from 2000 to 2005, okay. CML. Chemical Markup Language. This sounds good. This sounds a bit more codey. Is an approach to managing molecular information using tools such as XML and Java. It was the first domain-specific implementation based strictly on XML. First based on a data transfer, what is that? Document type definition, yeah, I knew that. And later on an XML schema. The most robust and widely used system for precise information management in many areas. It has been developed over many years, but chemical information is traditionally stored in many different file types which inhibit reuse of the document. CML uses XML's portability to help CML developers and chemists design interpretable documents. There are a number of tools that can generate, process, and view CML documents. Also can distribute. CML, I like it. Okay, these systematic chemical names can be converted to structural formulas and vice versa, but chemists nearly always describe a chemical reaction or synthesis using structural formulas rather than chemical names, because the structural formulas allow the chemist to visualize the molecules and the structural changes that occur in them during chemical reactions. Lewis structures. Lewis structure. Molecular phenomena. Phenomena. I actually would like to look that up. Define phenomena. Facts observed to exist or happen. No, that's phenomenon. The noun. Okay, it is that. Fair enough. Nucleus. Okay, bonding electrons. Bonding electrons and the nucleus. Okay. Envelope of high electron density. Oh, you can see all the little electrons here. Kind of subtly faded in there. And then you've got this bonding electron. Okay. Electrons and protons, so this would be a negative. Electron is negative, yeah. Lewis structures or Lewis dot structures are flat graphical formulas that show atom connectivity and lone pair or unpaired electrons, but not three-dimensional structures. This notation is mostly used for small molecules. Each line represents the two electrons of a single bond. Each line represents the two electrons of a single bond. Two or three parallel lines between pairs of atoms represent double or triple bonds, respectively. Alternatively, pairs of dots may be used to represent bonding pairs. In addition, all non-bonded electrons, paired or unpaired, and any formal changes on atoms are indicated. So this is a hydrogen with two electron bond, and then it's got another hydrogen with a two electron bond to the O. So this is H2O, and this is representing, what was it again, the two dots? Pair of dots. Alternatively, pairs of dots may be used to represent bonding pairs. So it says alternatively. All non-bonded electrons and any formal changes on atoms are indicated. Okay. Condensed formulas. In early organic chemistry publications, where use of graphics was strongly limited, a typographic system arose to describe organic structures in a line of text. Although this system tends to be problematic in application to cyclic compounds, it remains a convenient way to represent simple structures. CH3CH2OH. Ethanol. Let me see if I can draw that. So we're saying here, so you've got carbon, and it has a bond, three bonds, so it'd be 1, 2, 3 hydrogen, and then C is bound to another 2 hydrogen. CH. What's CH? Periodic table. CH. I think this is actually bound already, isn't it? Yeah, I don't think this is. Yeah, okay. Yeah. So these are already bound. What was that again? Shit. I've lost it. This one. It says carbon is bound to H3, and then carbon is bound to H2. Well, let's just see. Let me just see if I draw it out and it makes a bit more sense to me. Hydrogen, hydrogen, and then you've got oxygen is bound to OH and 1H. Let's start with the top up here, OH, and these are all bound together. I wonder. Let me see what ethanol. Yeah, I'd love to see how this actually looks. Okay, okay. Well, it's not that interesting, to be honest. So it'd be like that. Ha! Oh, this is cool. This is cool. Um, okay, let me try and draw that again. So we've got, so you've got, I think it put, what is it? The main one's in the middle. So C is bound with three H's. One, two, three. Then you've got it bound to one H, two H's. Here's the two H's. And then the O is bound with an H. Something like that. Let's go back to here. It's interesting how it goes off to the side. I wonder what it's trying to represent there. That it's not another main part of the sequence, I guess. What do I mean by main part of the sequence, though? I don't know. Because it means that it doesn't lead on to anything else, maybe. Like this is the end of the line. Parentheses are used to indicate multiple identical groups, indicating God. Parentheses are used to indicate multiple identical groups, indicating attachment to the nearest non-hydrogen atom. Parentheses are used to indicate multiple identical groups, indicating attachment to the nearest non-hydrogen atom on the left when appearing within a formula, or to the atom on the right when appearing at the start of a formula. I don't understand this. Parentheses are used to indicate multiple identical groups. Okay, that in itself I don't understand. So indicating attachment to the nearest non-hydrogen atom. So if I were to, so if you had, yeah, C H3 C H2 and then OH. Okay, so this is saying indicating attachment to the nearest non-hydrogen atom. On the left when appearing within a formula, or to the atom on the right when appearing at the start of a formula. So CH3 2CHOH. Let's try this one. So it says CH. Let me go a bit darker, it's a bit hard to see on your screen there. CH3 is in a bracket 2C, because the H is not on the left, I wonder. HOH, or, and they've displayed it as CH, which is this part, and then, oops, C because the H isn't on the left. Is that right? 3, so this part, and then let's see if I can finish this off. So I've got this, boosh, I've got that, boosh, so I need to now do CH is done, CH is here, but this is 2 of this, so this has to be here, surely. OH. Let's see what it's got. Oh yeah, 2-propanol. Okay, that makes sense, somewhat. It's really annoying me that it's not centered on my face, my beautiful face. In all cases, all atoms are shown, including hydrogen atoms. Let me just double check I've got this right. So parentheses are used to indicate multiple identical groups. indicating attachment to the nearest non-hydrogen atom. Indicating attachment to the nearest non-hydrogen atom. This is great. Let me record this. Revise this. Skeletal formulas are the standard notation for more complex organic molecules. Okay, let me just do a blood test for my diabetes. Feeling a little tired. We are looking good at 7.8, a little bit high. No problemos. Okie dokie. Okay, skeletal formers are the standard notation for more complex organic molecules. In this type of diagram, first used by the organic chemist Friedrich August Gekule von Stradonitz. It's probably not how you say his name. I don't know why I said August when it's August, but the carbon atoms are implied to be located at the vertices, corners, and ends of line segments, rather than indicated with the atomic symbol C. So just from having the lines present, the carbon is basically omitted. The carbon atom is implied to be located at the vertices, corners, and ends of line segments rather than being indicated with the atomic symbol C. Hydrogen atoms attached to carbon atoms are not indicated. Okay. This is very interesting because that means that carbon and hydrogen are like super common, which I'm sure everyone watching this knows, but I did not. Each carbon atom is understood to be associated with enough hydrogen atoms to give the carbon atom 4 bonds. Each carbon atom is understood to be associated with enough hydrogen atoms to give the carbon atom 4 bonds. The presence of a positive or negative charge at a carbon atom takes the place of one of the implied hydrogen atoms. Hydrogen atoms attached to atoms other than carbon must be explicitly written. Okay, I didn't quite understand all this. So let's take... Wait, what was this one again? Condensed formulas. Condensed. Oh, let's give this another color. Condensed. Whoops. And this one, which I quite like, is the Lewis structure. Oh, actually, let's see if I can rewind a bit, because I think I've got it written here already. Undo all the things. Ah, I can't get to it. That's a shame. Fine, condensed. Lewis structure. Formula. And this is going to be, so for this one it would be CH, so C is bound to H, and then C is bound to H3, C is bound to H3, two times? I don't know. Like this? And then it's O bound to H. Something like that? Ooh, not sure. Let's see what this actually is. This was propanol. Let's have a look how they lay it out. Oh, so this is using the other one. This is the skeletal formula. Let me record these. Intriguing. Skeletal formula. And I want to look at isopropyl alcohol, which in this case is that, but let's see if it's got the other way of drawing it. No, it does not. Isopropyl alcohol as Lewis structure. Okay. Ah, no, that's interesting. So it has the C. Oh, that's really, really interesting. Damn. Propanol, one propanol, but I think I've got two propanol. Uh, Let me just look at this again. Two propanol. That one. It's actually got a link for me. Oh yeah, we found this, right, yeah. Lewis hasn't got that. Smiles, yep, we'll have a look at that one. Okay. Now I'm starting to understand these. It doesn't have a Lewis for this. So it looks like maybe Lewis is sorry, Smiles is the one that people use. Smiles and these ones. Uh, Anything else? No. 2-propanol as Lewis structure. You tease. You absolute tease. Ha. Well, let's try and make sense of this. If it were this, then you've got the three H's on a C. We definitely have that. Then we've got three H's on a C, so we've got another one here. And then we've got a C with an H, a C with an H here. And then we've got an O with an H here. I mean, I guess that's... But they've defined it with this double dotting. I can't quite recall what that means. Let me go back. This is all good information. Two or three parallel... Okay, yeah, okay. Two or three parallel lines between pairs of atoms represent double or triple bonds, respectively. Alternatively, pairs of dots may be used to represent bonding pairs. Okay, so in terms of this, this is denoting that special relationship here, this double bond, I wonder. So let's just try this again. So we have our C, we have our C, we have our O. But we can define this as the single H, because then that allows us to give three H's over here. So now we've got this lovely bond for this one. But then, dear, so I don't know, because if I want to represent this double thing here, I would instead want to do the double bond here. And this is actually on the OH. I don't understand it. So this makes sense to me. So you've got the 3, you've got another 3, then you've got the carbon with the hydrogen bound to the OH, and that's it. Yeah, this makes more sense to me. Okay, let's not stick so long for here. But what I do want to do before I move on is go back to a Lewis structure that I know. So let's get one of these bad boys out. Oh no, let's do the, was it hydrogen with 2 H2O, so it's oxygen with 2 hydrogen, oxygen with 2 hydrogen, like that. H2O. Yeah, I think so. Lewis structure for oxygen, for H2O. See, why does it need the dots there for this? The double pair. It's like it's already denoted by that. I'm missing something. Let me try and read this a bit better. Lewis structures, also known as Lewis dot formulas, Lewis dot structures, electron dot structures, or Lewis electron dot structures, are diagrams that show the bonding between atoms of a molecule, as well as the lone pairs of electrons that may exist in the molecule. A Lewis structure can be drawn for any covalently bonded molecule, as well as coordination compounds. The Lewis structure was named after Gilbert Lewis, who introduced it in his 1916 article, The Atom and the Molecule. Lewis structures extend the concept of the electron dot diagram by adding lines between atoms to represent shared pairs in a chemical bond. Lewis structures show each atom and its position in the structure of the molecule using its chemical symbol. Lines are drawn between atoms that are bonded to one another. Pairs of dots can be used instead of lines. XX electrons that form lone pairs are represented as pairs of dots and are placed next to the atoms. Excess electrons that form lone pairs are represented as pairs of dots. Okay. Although main group elements of the second period and beyond usually react by gaining, losing, or sharing electrons until they have achieved a valence shell electron configuration with a full octet of 8 electrons, hydrogen can only form bonds which share just 2 electrons. The total number of electrons represented in a Lewis structure is equal to the sum of the number of valence electrons. In chemistry and physics, a valence electron is an outer shell electron that is associated with an atom. It's an outer shell electron that is associated with an atom, and that can participate in the formation of a chemical bond if the outer shell is not closed. In a single covalent bond, both atoms in the bond contribute 1 valence electron in order to form a shared pair. I don't know, it's too much now. Let me just continue. Skeletal formulas. Let's draw one of these. Okay, too much for now. Okay, skeletal formulas. Skeletal formulas are the standard notation for more complex organic molecules. In this type of diagram, first used by the organic chemist, this guy, the carbon atoms are implied to be located at the vertices. They're implied. So, just as a quick sketch, if we had CH2O, what's CH2O? CH2O. Ha! Nothing. CH chemical Yeah, CH2. If we had CH2 for, what is that? Methylene, dihydro, dihydrodocarbon, whatever. Okay, if we had that, then in this case, it would just be H. The carbon atoms are implied to be located at the vertices, so like that. 2H though. Carbon is bound to 2H. So carbon is bound to like this. Oh, here we go. There's one down here I can have a look at. Located at the vertices, corners, and ends of line segments, rather than being indicated with the atomic symbol C. Hydrogen atoms attached to carbon atoms are not indicated. Hydrogen atoms attached to carbon atoms are not indicated. Each carbon atom is understood to be associated with enough hydrogen atoms to give the carbon atom 4 bonds. The presence of a positive or negative charge at a carbon atom takes the place of one of the implied hydrogen atoms. The presence of a positive or negative charge at a carbon atom takes the place of one of the implied hydrogen atoms. Hydrogen atoms attached to atoms other than carbon must be written explicitly. So CH3, let's see, 1, 2, 3 lines. Then you've got this bound twice. CH 3 1 2 CH2OH. Oh, this is difficult. Gosh, someone who wrote it thought this was clever, so I need to persevere. Let's go look at something more simple. Skeletal formula for CH for oxygen for H2O. And this is definitely skeletal formula. For more complex molecules, I guess there isn't one for this. That makes some sense, I guess. Okay, fine. Let's put a question mark here. I need to understand this more, I'm sure. Indication of stereochemistry, hard chemistry, solid chemistry. Several methods exist to picture the three-dimensional arrangement of atoms in a molecule. Stereochemistry and skeletal formulas. Chirality in skeletal formulas is indicated by the Natal Projection method. Solid wedges represent bonds pointing above the plane of the paper, whereas dashed wedges represent bonds, pointing below the plane. Oh. Stereochemistry and skeletal formulas. In skeletal formulas, this is the complex one, chirality is indicated by the Natal Projection method. Solid wedges represent bonds pointing above the plane of the paper, whereas dashed wedges represent bonds pointing below the plane. So these wedges here, plane of the paper. Natal projection. The Natal projection is a way to depict molecules with complete stereochemistry in 2 dimensions in a skeletal formula. This concept is named after Giulio Natta. In a hydrocarbon molecule, with all carbon atoms making up the backbone in a tetrahedral molecular geometry, the zigzag backbone is in the paper plane. What's the paper plane? Ha! Yeah, that. Chemistry. Chemical bonds depicted as solid line segments. This is no longer going. I need to have a rest. So this was fun though. I've learnt a lot. Oh, 1 hour 41, that's why. Let me take a picture of this. I think we're going to do this next time. We're getting somewhere. We are actually learning. We are learning. Yeehaw! So, why did that do that? Let's cut that instead. Alright, to be continued. To be continued. That is super exciting that we started to figure out the periodic table. We did, yeah, okay, what we did. Let's do it. What we did. Periodic table, and I found this nice periodic table here. No, not there. That one there. It's pretty sweet. And then we discovered that discovered atomic numbering, protons, electrons, neutrons. We started to look at a tool that might be good to plot chemical structures, and it was, I think it was on this page somewhere. Yeah, this one, Chem Spider. Perhaps use this tool. And then we did looking at chemical formulas and structures. We learnt about the skeletal formula, needs more revision, sorry. We learnt about the what was it called? The Lewis structure, okay. Lewis structure made the most sense so far. And the other one, what was the other one? Condensed formulas. Condensed formulas. Delete that. That was crap. What we did. And then what we want to do next week, next episode, not next week, is continue reading this wiki. Try and draw some of the components of the nucleic acid. Alright, cool. Well, thanks for watching if anyone did. I don't think anyone did, but speak to you another time.